All right. Hi. Hello. Happy Thursday. Thank you for coming. A few reminders for you. First, I sent out an announcement that the video assignment is all ready. Let's go over that really quick. So that's my announcement. Let's go down to the video. And we've got the document here. Make sure to read it carefully. So a lot of things are similar because things can be copied over from video to video, but the wording has kind of been updated for what you're doing in this project now, which includes first, your entire group has to meet to figure out conceptually how are we solving the problem. So this is not because I don't want just the architect to be responsible for this. Like that's the situation I do not want to have happen. So the entire group must meet to figure out how are we solving the problem. And then the entire group has to write the pseudocode for how are we going to do this. And so once you've got that, then we can break it down into the 3 roles. So there's more of the group component at the beginning to, to solve the problem and do all that work. So the architect from there is responsible for, in the slides, having the pseudocode, having graphics and explanations. So this includes coming up with some toy data that demonstrates and maybe walk it through with this small example. So maybe only 3 or 4 data points. You'll see this in a lot of like YouTube videos when they're like, let's explain the knapsack problem. And they'll give you like 4 items. So yeah, so small examples that demonstrate how the pseudocode is working, how the algorithm is working. And then, as usual, drawing pictures or animating slides to demonstrate here's how it works. And then also describing the efficiency. So once the whole group comes up with the pseudocode, the architect's job is to come up with an example and be able to explain it. From there, the programmer, you have the pseudocode, then implement it. So depending on what language you use or how you structure that data, it should be fairly straightforward once you've got the pseudocode. And so tested on both the toy example that the architect comes up with and the standard non-trivial data. So something that is bigger than just this small example. And then the rest is standard like we've had previously. And the videographer is also standard as we've had previously. Let me scan through and see if there's anything else that I forgot. Yeah, something that I see in multiple people's videos is if you put the GitHub link in the YouTube video, sometimes it gets cut off by ellipses. So just verify once you post it, like open the link in an incognito tab to see whether the link is there and you can click it or not. Yeah, that's something I've seen across multiple submissions. Yeah, okay, so the standard notes, if you've got a question on those, let me know. So there's, I think, 4 problems that I assigned and a 5th optional one. So the first problem is longest common substring. And this is, so there's a thing where we have 2 words and we want to find what's the longest substring that is in common with both of the words. So photograph and tomography, the longest common substring is ograph. And so the question is just how do you figure that out? The parentheses bonus question is you've got this arithmetic expression and you want to figure out how do you parenthesize it so that you get the maximum value out of that expression. So that's a dynamic programming question. For a city grid, you've got a street in an XY grid, or a city in an XY grid, and there are some bad neighborhoods, and you want to avoid those areas. And so it's a dynamic programming problem to figure out how do you get from the top left to the bottom right. Then there's the time traveler, which is where you come back from the future, where you have some array that tells you here's the price of Google stock, and you want to use this information to make a lot of money, but you're only allowed to have at most one transaction per day. And so figure out how you buy or sell stocks in order to make the most money. So those are the problems that I have assigned. There's an optional problem, which the book says it a little bit is harder than the other ones. So I tried to, these problems come from the book, and they're all roughly the same amount of difficulty. But this one is a little bit harder. But if you don't like the problem that you have, or it's too complicated or just isn't sticking with your brain, then you have the option to choose two-player game instead, which is if you've got some n-digit number, with each move, you're playing against someone else, and you can choose either the first digit or the last digit, and then add that number to your score. And then the other player can do the same thing. And so the question is, how do we find the best possible score for the first player? Okay, so those are all the problems. Also, I'm here to remind you that the group assignments are at the Google Sheets link, and something that I still see on the second video is that some people didn't submit the collaboration form, which just tells me how well you work together. And so I have to take points off if people in your group didn't. So make sure that once the videographer submits it, maybe it's the videographer's job to remind everybody, hey, fill out the form. Get us all those 3 points. So then here I've just screenshotted. Here are all the problems again, just in case. Any questions on the video? Okay, so your job is to meet with your group and solve your problem, or decide if you want to take on the two-player game instead. All right, so that's your job for the video. Make sure you're still working on the project. The second progress report is due tomorrow night. And then continue to work on the packet problems outside of class. So whatever, we'll get to some point, and it's your job to go home, maybe meet with your colleagues and think about it. How do we continue this work? All right. Okay. Designer, go away. All right, so my plan is generally to keep working on Packet, but I understand that dynamic programming is hard. It's also hard for me, right? Like, it's a way to conceptually solve a problem, and it's really, really difficult. So it's going to take all of us multiple shots at this thing. So my plan is I will go home and do some more research, and if I have interesting things to tell you, I'll bring them back and we'll talk about them at the beginning of class, which I've got some things today. So I found several YouTube videos, which I link. Nope, that's going to make us go through the whole thing. I found several YouTube videos which are linked in the new version of the presentation. And so I'm citing my sources as I go. So if you want to go and watch those videos, feel free. So one thing of we talked about dynamic programming being a combination of recursion and writing stuff down. So, and for recursion and writing stuff down, that tends to be memoization, where as we recurse, we write down, here, we've solved this, or we check if we solved it, and then don't do recursion anymore. That's one option. The tabulation or bottom-up approach maybe doesn't use recursion. So that's the situation where we have an array or a matrix and we fill it up. So because when we do memoization, we end up filling up that information anyway to calculate all those things. So tabulation says we're filling this array anyway. Let's just do it without recursion. And so the benefit to that is if there's a lot of recursive calls, then tabulation avoids that because that can trigger system constraints if we have too many recursive calls. That doesn't mean that we can't use recursion with tabulation. The smaller subproblems may still do it. It just kind of depends on how you decide to implement it. Okay, so memoization stores the results as we go, and the recursive call, the job of the recursive call is to break it up into smaller increments and then build up once we have recorded those things. So we're doing the same thing of solving small instances and building up. It's just recursion or not recursion. Different ways of doing it. So yeah, so the number of recursive calls, that might be limited. And so if you expect a large amount of recursive calls, then maybe go for tabulation. But it also depends on like what makes the most sense in your brain as you're approaching these problems. Okay, so I found a YouTube video that breaks down, here are some steps to approach these problems, which I found really interesting. So I want to share those with you. Step one is to visualize the problem. So that can mean if you have like so the first problem on our list is you are a popular actor who is offered N job. They have a start date, an end date, and a salary. And so like write it down, come up with some examples, figure out how, because if you're given a general question, you still want to have, especially for the video, you want to have like code that you can run. And so being able to come up with some data and then maybe visualizing it in another way. And so I have some slides in a moment, which shows like you can adapt it to a graph or come up with a matrix and fill some things in. So being able to visualize it instead of just trying to like keep it all in your head, visualizing is better. And the other thing is you need to be able to focus on one thing at a time. So being able to start small and build up, that's the idea of recursion, where we break it down into the smallest possible instances and then build it back up. So being able to focus on one thing at a time, so you're not having like all the 50 other different variables that you're trying to optimize for, focus on one thing at a time. The next step is we have to find an appropriate subproblem, which means how do we break this big, large problem down? And so there's some strategies for ways that we can visualize it. And so in general, it's we take it away one at a time or build it up from scratch. So any way that we can figure out how do we reduce that. The next step is to find the relationships among the subproblems. So once we have a subproblem, how do we use that solution to apply to another? So if we're here, how did we get here? What other things did we need to know in order to get here? And as we go, you'll pick the best performing subproblems. And so once we do that, then once you have that with an example, then you can generalize. So take the, we'll see the knapsack. And so you can take, oh, I did this example. Now I can generalize it. And so say for any list of items that I have, or for any weight that the knapsack can carry, here's how my algorithm works for that. And then you implement it by solving the subproblems in the order that you need to. So for the adapting to another format, I thought this was really interesting. So the video that I got this from is looking at the longest increasing subsequence. So given some sequence of numbers, we want to find what's the longest increasing subsequence. So starting at some number, so like 3 and 8 is an increasing subsequence, but the question is it the longest one? And so it turns out that the longest increasing subsequence is 1, 2, and 5 with a length of 3. And so one of the ways they chose to visualize that was with a graph, where we can do this topological sort that we've talked about with graph algorithms, and then we just find the longest path. There's an algorithm for that. So we know some things about graphs, so let's use that. Especially the directed acyclic graphs tend to be useful in dynamic programming problems. So they have another example where they've got this list of boxes. Each box has a length, a width, and a height. And the question is, how can we stack boxes so that we have the tallest stack, but also that it's like a pyramid, right? So you can't put a bigger thing on top of a smaller thing. And so the way they visualized it is, here's a graph where this box can be stacked on top of this box. And so then they break the problem down into, what if we stopped at this box? Or what if this one was the bottom box? And so as you go through that, then you can find, here's that longest path. So then there's some examples for how can we break into the problem into subproblems. If we're given just an array, so then you look at only part of the array. So either start at the beginning and build up, or go from the end and break down. You might need to sort it first if you're given something that's not sorted. And then similarly, if you're given two arrays, maybe holding different information, the same kind of thing, but maybe you need two variables to keep track of if they're different sizes. Sometimes you might need to not break down from the end, but maybe expand from the middle. That could be a possibility. Or if you've got a matrix, only look at part of the matrix. And so, yeah, so being able to limit yourself, so you're not looking at this whole big, complicated, overwhelming problem, break it down into small, solvable instances. Okay, so I found this matrix which shows the edit distance for two words. And this is an example of how we can build up this matrix. So we can go row by row or column by column to get this information, so the zeros are, there's nothing needed to do to change this into this. So to change the empty string into the empty string, we don't need to do anything. To change a T into a T, nothing needed. But it goes on to where, so like down here, so down here, this is a 9 because we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters so far. And that means we have to do 9 deletions to get back to the empty string. But if we're building up the strings one by one. Going up to technolog, there's no changes needed. So these just intermediate things are just how do we change like tech into let's take this one. So to change techno into tech, we just delete N and O. And so you fill in this matrix as you go, row by row, column by column, and you get eventually that over here you need 5 changes to change technology into technological, which is just change this to a Y and then delete these 3. Or change this to an I and then add 3 more letters after that. Okay. That's edit distance. For the knapsack, the brute force way to do the knapsack is to take each item and ask, do we include it? Do we not include it? And so then if we include it, then we ask, what about item 2? Do we include it? Do we not include it? But we have to also consider the case if we didn't include item 1. So this sort of thing, this is what like calculating all subsets of however many things we're putting into the knapsack. And so that's not recommended. So as you start approaching these problems, maybe stop and consider first, are you doing the brute force approach? Like, can you draw a tree like this? And if you can, then we need to rethink how we're approaching it. So yeah, so the other option is to put some of these things in a matrix where the rows are, here's what items I can choose, and the columns are, here's the capacity of the knapsack. And so the bottom-up approach is to build this thing row by row with the options that you have for each item. So I've got an example here. I think, okay, I'll draw on this. And so, no, I think I want to type. So this is assuming we can only have one of each item, which is an important caveat. Okay, so the way that we approach this is again, we're starting with we're considering the knapsack capacity. So we start small and then we build our way up to, let's say it's 7. And so we start with, let's say we can only hold 1 pound of whatever. And then we start with the first item. Item 1 has a weight of 3 and a cost of 50, but we can't do anything until we're actually there. So if we write down the cost, we can't include anything for capacity 1 or 2. But for capacity 3, now we can hold item 1. And so we write 50, because now we can put $50 worth of things in our bag. And then for the rest of it, if we're only working with item 1, there's nothing else we can do. So however big our knapsack is past 3 pounds, we can only put 1 of item 1. This is our key assumption, where we're assuming we can only hold 1 of each item. So that carries over. When we have item 2 in the mix, again, for capacity 1, we can't do anything. But when we have capacity 2, now we can have 2 in there. And if we have item 2, that's $40, which is worth more than $0. So we absolutely want to choose having item 2 over having nothing. For capacity 3, we could include item 2, but $40 is less than 50. So we don't do anything. And we just retain what the previous row has calculated as the best option. Capacity 4, again, we can't have them both, so 50 wins. But for capacity 5, we can have both of them because 2 plus 3 is 5. And so 50 plus 40 is 90, which is better than 50. So we take that. And then same goes for 6 and 7. Then for item 3, so again, we can't do anything. At this point, we can't store item 3, and so having only item 2 is better. Again, at this stage, we can't do better than the previous row. Once we get to capacity 4, $70 is more than 50. And then for 5, if we choose item 3, we cannot, then it would only be worth 70, and that's worse than 90. So we make no change. And now here, capacity 6, we could have 4 and 2. 70 plus 40 is 110, which is better than 90. Wait, no, this is 3 and 4. Nope, 2 and 3. And then capacity 7. So we could have 3 and 2, which would give us 110. We could have 3 and 1, which gives us 120. Which wins. And so we keep going, right? So this item has a weight of 5, so we can't do anything with this item until we get to capacity 5. So those are all copied from previous columns. And so now here, we could only have 5, item 4, which would give us weight 80, but that's no better than 90. So we keep that. And then here we could have item 5, but we don't have anything with a weight of 1 to compare it to like add it to. So we can't do anything better. And then here we could have 5 plus 2, 80 plus 40, which is 120, but that's the same as what we had before. So if we wanted to, we could write it down, but since it's the same cost, I would maybe just keep what we had. Okay, so now we've got item 5. And so if our knapsack only has capacity 1, we can choose that. Great. We finally have an option here. Capacity 2, the best was $40, and we can't beat that. Capacity 3, we could do 10 plus 40, which is 50, which is the same as what we have. So maybe just leave it. Capacity 4, we could do 1 plus 3, which is 60. But that's not better than 70. Capacity 5, we could do 1 plus 4, that's 80, not better than 90. And then the other options, since we looked at those before, are also not better. And then similarly for these, we find that 120 is going to be the best we can do. So once we fill out all the table, we find that this combination is the winning one. So we start at the beginning at the first row and we build out, right? This is the finding the subproblem where we start with the one item and one capacity and we say, can we fit this item in the knapsack? And then we build up. Okay, any questions on that? Okay. This is my references list. This is the one with the different steps. This is the one with the knapsack example. And okay, yeah. And when we come back on Tuesday, I might have more slides for you as we go and figure this out together. Okay, so with that out of the way, let's go to in-class packet. So maybe let's take a few minutes and try and think about the actor thing. Wait. No, I had one more thing to tell you. All right. So I looked this up on ChatGPT just to be curious, see what it gives me. Can you explain a dynamic programming approach to the following problem? And yeah, it gives me, here's how the problem breaks down. Here's the key idea. Here's the step-by-step plan. And then it gives me pseudocode. Great. The problem is if you did this with your group, the thing about dynamic programming is getting to the solution and getting to the pseudocode that's the creative process. So this has us like pre-compute something and store it in array. I don't know how that works. I would have to sit through the code and go through it step by step to figure out here's what it does. So there's mental work that I would need to go into this solution to figure out how does it work so that I can understand it and be able to explain it, because that's the point of the video. One of the things it doesn't have is like, if we talk about storing something as a graph, it doesn't have that. So I could have chosen a different way to approach this and something that the AI didn't give me. So as you talk with your group mates, keep in mind that AI could give you a solution, but it's almost certainly not the only solution. And maybe it's more complicated than you think. Yeah, there may be a simpler way that makes sense to you. So that's my caveat, where it could give you something, but is that the route you want to go down? Something to consider. All right, let's take maybe, I don't know, 5-10 minutes, and let's talk about the actor job again. Maybe going over the tabulation example helped solve this problem in your brain. Talk with your neighbors and work it out. Any questions before we break off? All right, let's go. Okay, I just want to bring us back. So we've got about 10, 20 minutes before class is up. So we're all kind of working on different things. And so what I want us to do is kind of share. And so someone's working on something that probably may work. Another person may be having trouble understanding. So I want us to distribute this information and try and come to a consensus. And I say this knowing that a few groups have something that's getting pretty close, but it's a different, like it's structured differently, but it gets to the same idea. So I want us to go around and present it. So I'm going to pass out markers. So while I do that, discuss with the people you've been working with, or if you've been working by yourself, that works too. So what approach are you using generally? So is it memorization? Are you using recursion, or are you doing tabulation or something else? How are you visualizing the data? So are you using a matrix or a graph or something else? And then what's your step for how do you break down the problem? Those are the three things that I want to know. So maybe if you've got a graph, or how you're visualizing the matrix, I would like to see maybe something like, so for knapsack, it would have been like items and capacity. And so we do it first by each item and then increase the capacity, and then we go down the items list. So that's how I break down the problem. That's the information that I want. Does that sound good? Okay, so talk with your group or with yourself of this is how I'm approaching it. If you get stuck at one of these places, then just say that. But yeah, I'm gonna go ahead and distribute the markers. You can use them if you want, or you can just say it visually. All right, so finish up as you can finish up while I'm talking and while others are talking. I wanted to bring this up that, so we've mentioned longest path. So there is a problem called how can we find the longest path in a graph? The issue here is that if it's a directed acyclic graph, then we can find it. If it's not a directed acyclic graph, then the problem is NP complete, which is code for really, really hard. So keep that in mind. So that's why dynamic programming, we try and structure things as a directed acyclic graph, because then we can do topological sort and do all this fun stuff. So that's what makes it possible. Okay, I will take notes for how we're doing this. Who wants to go first? Go for it. Mm-hmm.
That's right. The vertices of these dogs, and then this would be this. They're connected if the jobs still overlap. Some issues we thought of is that they may eventually overlap, but simply aren't connecting the jobs. And that you may result in less money compared to if you were to just take a bunch of smaller.
Okay, so I'm confused. May eventually overlap. Mm-hmm.
We go through the path and eventually like the job and maybe overlap with that first.
So like, so if we have job 1 and job 2 and job 3 and job 4, we can take 2 after 1. Maybe 2 and 3 overlap. But you're saying there's a possibility that 4 could overlap with 1?
Like if for example, if like job 3 like starts like 10 days before job like 4, but job 4 it's a long time overlap. The first job and job 1.
So you're thinking like job 1, job 2, and then job 4. Yeah, so this would mean that there isn't an edge from 2 to 4 anyway. Then there would be a situation where, or actually it would go from 4 to 3. Yeah, what I would suggest for this is come up with examples and draw out the graph and see if this problem that you're thinking of, if that arises. Okay, next group. Go for it.
So we also started by sorting the lists by start date, or the starting value. Then we're gonna have two values, A and B. We said the earliest job is A, and then we iterate through the subsequent jobs. With each of the subsequent jobs being iterated through all these, so it gets reset as we go through each iteration. Then you check if the timeline of A and B intersects. And if B, then you then check if B has a greater pay over time value than A. And if it does, then B becomes A and you pass recursively. Then else, if the timelines of A and B do not intersect, you save A in the final list, and then you pass B recursively as A.
Yeah, okay, so my concern is that maybe we have a list of 12 jobs, like one per month, and we could take all of them. Does this allow for that?
The 12 jobs.
Yeah.
Yeah.
Is A and B are like a list of,
It's like kind of two points. Just once you're done, so you go
okay,
like kind of evaluate A, see if there's any jobs that you kind of king of the hill. You know, you're seeing like, which is like the best starter thing. And then once you reach the point in the list where like your highest value starter job is no longer intersecting with any of the other jobs, then you just say that, oh, then A is no, there's no jobs that are going to contend with A, so you just save A. And then you reset with B is A, and then you kind of see if there's any, you kind of go through the potential contenders. And then once you kind of evaluate the highest value contender, and then the timeline runs out between like the end date and the start date. Subsequent ones. Then you kind of just rinse and repeat past B is that A. Just like you're kind of only holding like two jobs at a time as you're going through the entire list of jobs.
okay. Yeah, okay, I can see that. Any issues you think might arise from this? Yeah, okay, I recommend doing that. Okay, next group. In the back.
It's like, I guess it's all down the road, but we're like, get by giving the value of the job and then dividing it by the end of the start, taking the value and dividing it by the time of that job. And then you divide it by only the resource efficiency, which is having a list of priorities. So the one that is most value has priority. And it's like the breakdown of it would be like choose the most efficient value. And then we go to the next value and it be the conflict in terms of time. And if there isn't, then we add that to a job we want to think. If not, we move on to the next value and then we can do it. We're prioritizing and time. And in this way, we saw it make the most money because they're taking jobs then that have a high value for, and it's not giving too much space in the overall time to do the job.
Okay. I want to mention very briefly that so priority queue is a data structure that imparts some information where we can NQ and DQ things. Yeah, I just want to make sure that we're not confusing it with just like a sorted list. Where like the point of the priority queue is like we can NQ something and then DQ the thing of highest priority. And so like it's kind of the same thing, but it's also kind of not. Where a list is just here's a collection of things and we can sort them by whatever value. So just keep in mind the difference between those. Yeah, I think so. Yeah, and so the question is, what would be more efficient? Like, do you need the priority queue, or could you just sort the jobs based on efficiency? I would maybe argue that sorting the jobs is all that's needed. But if you are like, no, we need the priority queue for XYZ reason, like maybe we're adding jobs later, then those would need to be higher priority. Maybe something like that. Okay, cool. Next group. Go for it. Mhm. So each thing is a job. Mhm. Yeah, cool. I think that sounds fine. Okay. How much time exactly do we have? Not that much. Okay. Thank you for everyone who wrote something up on the board. Um, what I might have you do is go and write pseudocode for this. So take this home and if you've got a winning solution, write pseudocode for that. If you don't think you have a winning solution, maybe adapt one of the ones that you heard. And we'll come back next time and we'll talk about it. So we're spending a lot of time on the interval scheduling job just because dynamic programming is hard. So let's work on one problem and make it good. All right. Thank you. Send me your project progress reports by tomorrow, and I will see you on Thursday.